the idea that the universe started from something and is now what it is, we seem to want some sort of explanations to how that could possibly be. So the fact that some people have a number saying, well, you know, the Big Bang was the universe is expanding this fast, and then another group of people say, no, the universe is expanding this fast, and they're not telling each other that the other group is wrong. They're just saying, is my numbers are this. The group says, my numbers are this, and within the last a few years, it turned out that the groups were finding that each of their numbers was right. They were both right. So there are two groups of people who have been working on the Big Bang. There are people who we refer to as the early people. These are the people who are literally looking at the Big Bang, because we can still see the Big Bang, the afterglow of the Big Bang. They look at the afterglow of the Big Bang, and they can determine an enormous number of things about the universe, which is mind-bogglingly too many, such as the amount of matter in the universe, the amount of dark matter in the universe, the amount of dark energy in the universe, the amount of, well, there's just a long list of things that they know based upon stuff that I've told you before. So without telling you too much about the stuff I told you before, cosmic microwave background radiation, I'm just going to say those guys came up with some numbers, and these numbers on this graph here, these numbers are shown with error bars. And the thing about these error bars is these error bars have gotten smaller and smaller over the last decade, so that their measurements no longer overlap the other group of people who are using an entirely different and completely unrelated set of ways of doing things. And they're the people, they're the late people. And they look at the universe starting at where we are here and looking outwards, whereas these guys are looking at the end of the universe and inwards. So the late people also come up with numbers. They have error bars, and it turns out that for the first time ever, those error bars don't overlap. Maybe something will happen, and the universe will, and they'll find something that will change the fact that this is beginning to be serious. The problem is these guys don't agree with these guys. They have different methods. There must be something wrong with one of their methods, or something's wrong with the universe. Yes?
Nothing is wrong with the universe. Something may be wrong with our present theory about the universe.
Much better said. Okay, that's exactly what I meant to say. Thank you. Yes?
And per Einstein, you have a wave and a string, and they're both accurate. So
Einstein never mentioned strings. You should know that.
Oh well, but there is both those theories.
No, Einstein. No. Einstein was right down. Einstein was right down the. He said, general relativity. I don't like quantum mechanics. I don't like all these newfangled ideas. I'm done with it. General relativity. I have an idea. I'd like to come up with some really new theory. He never came up with it. So Einstein, if you're mentioning as an example, this isn't a good one.
But whoever followed him posited both the string theory and the quantum theory, so that, and they both exist and they both are true.
No, again, not. String theory is not true. Quantum theory, if you will, is as true as any truth can be, until it's found to not be true. But the theory explains all the phenomena. The problem with string theory is it explains absolutely nothing. It's just nice. People have fallen in love with beautiful mathematics that couldn't possibly be wrong, and also cannot be tested. So far, no one has come up with a test of string theory, whereas there exist thousands of tests of quantum theory. So they're completely unrelated. I'd love to believe in string theory, but at this point it's a belief system. And scientists are not supposed to believe in things. And so so this is, if you will, this is a hypothesis. Here is an idea. Let's see if there's anything we can do to test it. Nothing yet has shown up to be that thing. It may never show up to be that thing.
So there doesn't exist notice my voice.
Yes, thank you.
There doesn't exist such a theory that two things that seem seemingly opposites or seemingly separate and different are actually also true at the same time. Oh, the cat theory is also.
What you're looking for is the wave-particle duality.
Wave-particle.
Okay.
Yeah.
The wave-particle duality is a well-established truth in science, which boils down to, on some level, without going into what it is, nature, and this is fair, nature has ordained that there are certain things that nobody, human, cat, or otherwise, will ever know about the universe. And it's a law of the universe. It's actually not a thing we will eventually know, so we don't know now, but we will. No, it's backwards. There's a law of the universe saying that there is something you cannot know and will never know, and that's the law.
That's bull. I mean, there.
Heisenberg uncertainty.
No, there's certain things that basically say, with this species, development, we don't see us knowing it in the next 50 or 100
No,
years.
you're wrong. That's bull. As long as you call what I said bull, I call what you said bull.
Can't somebody...
No, there's actually, no, really, this is the startling thing. There is a well-established law of physics that says that there is no way we're going to learn certain things. It's outside of not of our ability, but it lies outside of the laws of physics. There is no one ever, a million years from now, who's ever going to know this. And it's really because what it is what you want to know is where the electron is in the atom, okay? And there is these things called orbitals, and the electron is in an electron cloud. And you go, aha, I'd like to know where the electron is. If I had better instruments, surely then I could know where the electron is. And the laws of physics say, you can only know the probability of where it is at any given time. And as soon as you look, you will find it. You can always find it. You can always find it. You just can't predict where it is. You can find it, and then you can let go of it, and you say, okay, on the basis of the now better laws of physics that I now have determined, because I'm now 100 years more skilled in my physics, I can now know, having let go of the electron, where it will be in the future. So I now know those laws of physics because it surely has come to me now. That law of physics won't ever exist. You will never be able to predict where an electron is. It's against the laws of physics.
As we understand.
No, not as we understand it. Sorry. You can disagree with me all you want, but you're wrong. Okay? Just look it up. Look it up.
So
It's called the hidden value theorem. Okay? The hidden value theorem. You think that if we look more carefully and see some values that we don't know, those values will be able to help us predict where the electron will be. This hidden value theorem was written somewhere in the 1930s, so it's about 100 years old. Okay, no one's ever disagreed with it. Google it. You have a phone. Google it right now. Hidden value theorem. It says there aren't any hidden values. That's what it says.
I want to know what he is.
He's saying when we get more smart as a civilization, we'll know more about quantum mechanics. And I'm saying, no, sorry, sir.
All right, let's go back to something simplistic as an analogy. You look at what a caveman could understand about.
But it is an analogy.
Now we have an electron microscope, and we can really see some really small things.
But we can't see electrons.
Not yet. But the point is, if we advance as far up as from, I shouldn't say the cave people, 3,000 or 4,000 years ago, the Bronze Age people, they didn't have a clue If we
I
go
understand.
3,000, 4,000 years.
So you're
past,
reasoning by
we know
analogy.
that-
I'm not reasoning by analogy.
Okay, well.
I'm not reasoning by analogy.
Okay.
I'm not reasoning at all.
Okay.
What is your background?
Okay, I'm a retired physician.
Okay.
Subspecialist.
I'm a retired astrophysicist.
Okay, so it is, no, you, okay, if you're a retired astrophysicist, you know far more than I do about this. Absolutely. I will-
Hidden variable theory. In physics, hidden variable theories are held by some physicists who argue that the state of a physical system, as formulated by quantum mechanics, does not give a complete description for the system. There you go. An example would be that quantum mechanics is ultimately incomplete. There you go. And that a complete theory would provide descriptive categories to account for all observable behavior, and thus avoid indeterminism. Right up your alley, right? I didn't make that up. I just read it in Wikipedia.
but if
Okay,
you-
that's what you're saying.
No, I'm saying one thing. If you talk about Newtonian laws.
No.
one talks
Let me
about
read.
the
Let me read
Newtonian
on.
theory.
Let me read
No,
on.
They call it the Newtonian laws. When you talk about the hidden value theory.
No. Wait.
Different
Let me
theory of law.
read on. Okay. In another. Okay. Albert Einstein objected to the fundamental probabilistic nature of quantum mechanics. Okay. And famously declared, "I am convinced that God does not play dice with the universe." Okay. Now, early attempts at hidden value theories. See, so this is history of what you're talking about. This is not a physician postulating something. This is physicists who have PhDs and started in the 1930s talking about what you're talking about. Okay, so this is not a conversation that just came up for you. It's been discussed. So there's debates, incompleteness of quantum mechanics, paradoxes, Bell's theorem, and you know Bell's theorem, right?
I sure do. Not my field.
And bottom line, recent developments, 2001, published to prove. So this guy in 2001 published a proof that that any extension of quantum mechanics theory, whether using hidden variables or otherwise, cannot provide a more accurate prediction of outcomes, assuming that the observers can freely choose the measurement settings. Okay, so whether or not you agree with me, you better get on this page, okay? Put your stuff up on this page. They will let you type. They will let you type. This is Wikipedia. You can put anything you want up here. What happens is, when you do that, people who disagree with you, who have more say in the matter, get your stuff off the page as quickly as possible. So don't argue with me, argue with Wikipedia, all right? Right? I mean, listen, I love the question you're asking, and I love the fact that we're doing this thing back and forth, and I love the fact that I'm yelling at you because you're really asserting something that is so right to assert in the first place. And it is so logical. It makes so much sense because really what I'm doing here is I'm the authority in the room, telling you but what I'm doing as the authority in the room. See, I am a scientist. You're a doctor.
I'm a scientist too. Yeah.
No, but you're
biological science.
what kind of doctor? I mean,
internal medicine or rheumatology.
okay.
But,
So you have had at least 8 years of medical school.
medical school and post-medical school.
And
More than that.
yeah,
More than
you
that.
have been educated as well as anyone in this room, and your education and my education really are of a comparable nature. Okay, here's the thing about my education. I am not an acting scientist. I'm just some guy talking up in the room with a PhD. Okay. I attend from time to time, just like yesterday, lectures by people who really do science. There's a seminar at the Museum of Natural History. They do it every week or so. I go and I see real scientists doing real science. And you know what happens when I go in that room? I learn how little I know. It's lovely. I know an enormous amount of astronomy. I learned that I just know so little, because the people in the room who are active working scientists, who are active in knowing what's going on in the current world at the level of the original base papers that are being written, and I'm just reading, YouTube accounts and something published in the New York Times, and occasionally I go down to the paper. I know very little, okay? But those people don't. And when I see them working, and I see the work that they're doing, and I see the level of detail that they go down to, they're in that room, and those 10 people in the room who are at the seminar, they are going after them. They say, what about this? What about this? What about this? You see science being done right there, and it's really complicated.
I am well aware that I go to a seminar on my area, and they will bring in a guy who's working in the National Institute of Health, and his major research is to prove A equals B.
Right.
So his data shows A equals B. Then they bring the next guy in who's working in whatever small subspecialty of that area, and his laboratory has found that A does not equal B. And then they go argue with each other.
Yeah.
So I mean,
it's lovely, right?
Understand what they're talking about.
Right, but what?
We get back to
No, we'll get that. But the point is, and no, there is a relevant point here, which is why I went down this far. I have been studying this conversation that we're having here for 10 weeks, trying to be able to present it to you in some spectacular and cogent way, so that you could, understand it. But what I've come to know in this room is that all I can do is present the really fluff, the highlights, the cool stuff, the magic stuff at the top, and I have to leave the good stuff. For example, good stuff. You see these dots here? 1, 2, 3, 4, 5. Those are good. That's the good stuff. I could spend lectures and lectures on each one of these things, because these are different ways of calculating this one. These are all add up to one number, 73. Okay? These all add up to one number, 67. That's the problem. So I'm not going to discuss any of these, but I have learned all about this, and the more I learn about it, and I go deep and down, I'm going, because I doubt so much of what I'm saying, because it's the Big Bang. It's insane. Really, it's hard to get your head around. And the more you learn about it, the harder it is to get your head around. But when you see people who really know what they're talking about, and they really aren't idiots, because you're thinking at some level, who is this guy? Because it's the first time you've been to class?
Yeah, first time I've been to class.
Right.
I mean, that's interesting. But
who is this guy who's spouting stuff? What's his authority? And really, I don't have any authority. PhD gives me.
You're explaining something that is wonderful but not practical for the world at the moment in astronomy.
Well, people who need a practical, shouldn't be here for practical. But anyway, so.
I'll give you a practical probably later.
But anyway, so what I will do with remaining time, and the time will go on, is I will try to describe the rest of the thing that I haven't been talking about for quite some time, and I'll talk about it quickly, so that you can at least we can get to the end of this conversation. Then, when I come back another time, maybe we'll talk about what that one is, and maybe we'll talk about this one is. But this tends to put people to sleep if I talk about individual things. All right. So but this shouldn't put you to sleep.
Well, I want to know, if I may.
Yes, you may.
What is the difference between the two theories of the Big Bang?
Okay. So what we're going to do is, first of all, we spent 4 weeks on the early. Okay. And the early numbers reduced to one thing. This is the cosmic microwave radio background. This is the sound, the radio waves we get from the universe. That's what we see. The picture gets better and better the longer, the more better satellites we put up there. As the satellites get better, the error bars get shorter. At this point, this picture yields this picture. Now here is the data points that have been derived from this picture. I previously explained how. I'm not going to now. This is this. This curve here is based upon this data here. The number of atoms in the universe, cold dark matter, dark energy, Hubble constant, reionization redshift, spectral index. There is 7 properties of the universe here. And on the basis of those 7 properties, this is the graph that comes out of it. Now, by changing the properties, which I get to do by moving this sliders here, I can try to reach a better understanding, matching the data to the data. I really have to just do this because otherwise I really won't finish. I'm gonna, then I'll take that. And she was first anyway. So by moving these sliders, I get better and better
Resolution.
matches to the data. See, the data is getting better and better as I move it. And I can keep playing with this to try to match the data, but I'm just going to press the button that matches it. I'm going to press the answer button, which is down here, because I don't have time to fool around with it or tell you what I'm doing. I'm going to press the button which makes all of these sliders correct. And that is an example, not an example. We have a theory which matches the data that explain that every one of these things now have a number. The Hubble constant has a number, which is what we're talking about, by the way.
Is that
But
the same as Einstein's constant?
no, that would be dark energy. Okay, dark energy at 75%, 74%. That's the gravitational constant. But Hubble constant has to do with how fast things are moving away from us. And the further you go away from us, the faster things are moving away from us. And that, which is what the topic of this conversation is, that number is found here, and it's 73. But this is an old graph, so it should be, say, 67. Okay, because this was done when the answer was 73.
So what does that to do with the Big Bang?
This is everything. This is the entire Big Bang. Everything you want to know about the Big Bang is right here on this stage. Okay, and all you have to be is a PhD in astrophysics, or A or B, have a long enough attention span to learn what this is. Okay, neither of which is present in this class except for me. Yes. I'm sorry. But yes.
If you go, as far as I know, the theory or the reality is, from what they can say, everything is going away from us. Nothing is going towards us.
Right.
Well, on the average.
On the average of the
For instance, Andromeda is headed our way.
Okay. Would that, this may sound stupid to you, but would we be the place, well, put it this way, could we be misseeing something like people used to think the Earth was flat? Because we have to be in the center for the Big Bang, because nothing is coming towards us. Everything is going
Okay,
away from
so
us.
I'm going to rephrase part of your question. Could we be misseeing something? And I will rephrase it. Is there a systematic error to all of this data for which essentially we're missing something that we don't know that we're missing? Now that's always true in science as well as in every other field. Okay, so there is that possibility, and because I have been playing with for a long time, I actually, one of the things that I will probably discuss, but probably not today, is all the things that I think could be wrong with this. Because I'm the kind of guy who is a skeptic. I don't believe anything that anybody tells me ever, and so I have to be convinced. And I frankly have been becoming more and more convinced about the Big Bang, the more I read about it, than I ever was before. Here's one thing I just found out that is the fact that I learned it just this week, and that it's been common knowledge for 40 years, strikes me as being something that I didn't quite get. Everybody thinks that the Big Bang began as a singularity. Everybody knows that. Everybody thinks that maybe before the Big Bang, time didn't exist. That's a phrase you may have heard before. The space didn't exist before the Big Bang. You may have heard that before. Big Bang began as a singularity. You heard that before. Well, I heard this week that that's just not true. That's not what the Big Bang is. The Big Bang is some moments in time, a long time ago, where the universe exploded and did its thing, but that before that, there was still a universe. There was still a universe. That scientists think that the Big Bang came after there was something there in the first place, and that the thing that was there in the first place, called inflation, exploded the universe, but the universe was there in a small little place all by itself, not doing anything in particular, and not deciding to explode at all until at some point it did. And not only that, but we're not talking about just a millisecond before. We're talking about the universe could have existed forever, and then in this small region of space, it decided to explode. That is the most recent thing I heard this week, and I didn't hear it, I read it. And it made sense to me, and I could explain it to you. So now, raise your hands. Okay, you first.
One is, I don't know why you say that you're the only one who has the attention span to pay attention. But two, I've been invited.
No, because people fall asleep, that's all I meant.
Oh. Okay, I've also been invited to editathons, which is Wikipedia telling us to come and edit whatever.
Right.
And I don't know why you trust Wikipedia, because a lot of what's in Wikipedia is flawed people. A lot is flawed people and flawed information. So when you refer us to it, I don't let my students refer to Wikipedia material as research, because I think it's too flawed.
Okay, but what I've done on Wikipedia is I put in flawed information into Wikipedia to see how long it would stay.
Okay.
Doesn't stay long.
So correct,
Yes.
Now, I have a theory of the universe which is very different, and I don't want to go into it.
No, please,
What I
don't.
would like to say is that that little tiny thing you were talking about, how the hell did that get there?
But the space is infinite. There was a little place in it that decided to
How
explode.
did that get there? But my point is that scientists are really arrogant people, and that they don't accept the word mystery, and that mystery is what we're dealing with.
I disagree with you, arrogantly speaking. I arrogantly disagree with you. Scientists are all about the mystery. That's why they do it. People like me, okay, first of all, I'm not a scientist, right? I'm just a guy telling you stuff, okay? People who, the real scientists...
So is most medicine. Most medicine is arrogant also.
Well, that's not fair. Even though practitioners, but not otherwise. People on the cutting edge of science are all about the mystery. That's how they make their money. If you're out there saying, "Oh, this is true and this is true and this is true," you're a lecturer. Okay? If you're a scientist, you're out there going, "I wonder if this is true. Could this be true? Is there something wrong with this?" No, they're exactly on the edge of mystery. The most mysterious people in the world are researchers, scientists who are looking for what's new and different, and they will distrust everything in the interest of lining their own pocketbooks because they need to make a living, if nothing else.
That's right.
Right. So don't tell me that they're not mysterious. They are.
We once talked about the sound that you would hear when we had the old TV sets, and you would reach the 9th channel, and it was
Right.
a static.
Static, right.
And the same thing with the old radios. When you get in
Yeah.
between the stations,
Yes.
you would hear the sound.
Yes.
Is that the same information that you're talking about
Yes.
in that data? In other words, they've analyzed that sound now
The sound is right here. It's right here on this picture.
And there's nothing more they know about, more specific.
Well, they know more every year because they pay more dollars
But
to
that's
find
the
out more.
sound.
Yeah, and of course it's not sound, it's radio waves. But yeah, but they can turn it into sound. Because but it's basically the noise from the Big Bang is passing through our bodies as electromagnetic waves all the time. And if you point a telescope in that direction, you might get something that's a little bit brighter, and that's shown as red here. If you point it in that direction, you might get something that's a little bit cooler, and that's the blue over here. And it's all over the place. And the better the telescope, the more detailed that map becomes.
Do you believe in that little thing?
Do I believe in what? Do I believe in the data?
The
Yes.
universe existed before.
No. That's fair to ask. Do I believe in it? I have a lot of hard time believing in the Big Bang to begin with. Okay. So if you ask me, what is my choice of Big Bang? Do I want a Big Bang that began in a singularity? Or do I want a Big Bang that existed? Do I want a universe that has always existed, that will always exist, and is constantly doing things by creating something out of nothing? I am right here. I'm okay with the something out of nothing universe that was always here, and at some point it decided to turn nothing into something. And it turns out that nothing into something is something that you have already bought into. You have heard the word dark energy. And what dark energy says is, imagine empty space. There's nothing in it at all. Nothing. Remove everything. Nothing. Get it out of your minds. Nowhere, nothing. Nothing's in it. That's empty space is not empty. It has dark energy. What? Okay. Not only dark energy, but dark energy which is repulsive. We can push the universe apart. And not only that, but in the middle of the dark energy universe, everywhere in the universe, there is non-zero energy that literally energetic particles pop up and out of existence. Out of nothingness comes somethingness, and that's Heisenberg's uncertainty principle. If you can't see it, it's going to happen and it's going to happen without your knowledge. So near a black hole, if you have a little piece of nothingness right next to a black hole, and two electrons, one an electron, one a positron, appear out of nothing, because that's okay, because it's not against the laws of physics, because the volume in which it took place was so small that it violates the laws of physics for us to know what's going on inside. But we know, on the basis of that, the two things can appear for a split second. Split in the sense of quantum mechanics, so small a time that you can't measure it. Small volume, small time. Two electrons, one positive, one negative, can appear, and one of them can drop into the black hole and the other one can go whizzing away from the black hole, and you've just created something out of nothing. So something out of nothing is also within the realm of physics, and that something out of nothing explanation that I just gave you happens to have been invented by a little guy named Stephen Hawking, and it's called Hawking radiation, and the universe is filled with really crazy things. Black hole is maybe the craziest, not black hole, but Big Bang. And the idea that the Big Bang wasn't a Big Bang that created the universe, that it was just part of a larger universe in which this little section of it decided to become the universe, doesn't mean that another section of it over here isn't also becoming a universe. So it's often thought that if we believe in the Big Bang, we have to believe in other ones, other places, happening right now. Yes?
I've heard it described as bubble wrap.
Bubble wrap.
That
Yeah. Bubble universe. Bubble universe.
which would mean that there could be more than one universe.
Right. So basically, if you go down any of this conversation, you start to get into places that are really crazy, like the bubble wrap universe, which seems increasingly to make more sense than not, in some sense. You do end up in crazy places. By the way, do you want to put your name down on the?
Yeah, I will. Yeah.
Okay.
So how to get there in the first place?
So what we didn't discuss is this, okay, because we still haven't discussed it.
Yes, so it's
Constant.
What's that?
The constant.
Say again?
so it's for
Oh, yeah, you mean the
The attendant.
attendance sheet, yes. So really, let me quickly go down the other route, which is where we're really going to spend. We're going to spend more time on this. How do you know how fast the universe is expanding? First of all, you have to know where everything is in the universe. If you want to know how big the universe is and how it's expanding, you have to be able to point to that, and that, and go, well, that over there, that's moving at that speed, and this one, oh, it's moving at that speed, and it's this distance, and this one over here, that's moving at that speed, it's this distance, this one, that speed, and this distance. So once I've got all that hammered down, I got the answer. I got the Hubble constant. As soon as I have interviewed the universe in terms of how fast it's moving away from me and how far it is away from me, I'm done. I make a graph.
Oh, it's moving away from you.
Oh, yes. Okay, so I have something over here, and it is this is distance, and this is speed, v, velocity, and there's a dot. And I know this thing because velocity is easy to measure. You can just look at the change in the spectrum. So distance is the thing you can't measure. So how do I find distance? Well, different ways. That's on the screen there. That's what I'm going to talk about for the next few minutes. But so you measure the distance, and you always know the velocity because you can see it. You measure the distance again, and then you got another one. And you measure the distance of another object, and you got another one, another one, another one, another one. You're measuring the distance of things, and then pretty soon you discover that you've got a line. You've got a line, and that line, the slope of that line is called the Hubble constant. That line is it tells you how fast the universe is expanding. It's expanding at 73 megaparsecs, 73 kilometers per megaparsec, something like that. Which means that the further you go, the faster the speed. You had a question?
Yes, if everything is moving away, isn't it moving towards something?
No, everything is a big raisin bread. Okay, it's all the raisins in the raisin bread. The raisin bread expands. The raisins are not moving towards each other; they're moving away from each other. So the bigger the raisin bread gets, the raisins don't get any closer to one another. They're all moving away from each other. They're not moving towards anything. Yes, if you will, the raisins are moving towards the one that it's moving away from, but the one it's moving towards is moving away from it faster than it's getting close to it. So it never gets to catch up on the raisins in the raisin bread.
So it's like a balloon that's blowing up.
Yeah, it's like a balloon that's blowing up.
It's expanding in all directions.
It's dots on a balloon. Dots on a balloon. They get further and further away from each other. They're not moving towards each other. They're moving away from each other. Okay, so this is, we've discussed this many times. When I say that people don't get this, I mean that in this class, this same conversation can happen multiple times, and the same people in this class who are paying attention don't necessarily record it. There are some people who have heard it so many times they're bored, and there are some people who have been in the class just as many times haven't quite recorded it because it doesn't make sense to them. There are people who don't understand what I'm saying, and so I re-explain it. It's just what I do, and I need that sort of thing. I need things told to me 3 or 4 times anyway. So I'm part of the people who need it. I watch movies 3 and 4 times. I love them because they're great the first time. Great the second time, news to me the third time. Right? Same as with books. We're old in this.
Repetition is the mother of learning.
Yes. So what you need to do in this is the velocity is easy. What's the distance? The distance is called the business of figuring out the distance is called the cosmic distance ladder. And on this screen is remember I showed you all those different ways of doing things? Well, this is just a couple of those ways on the screen, and I'm going to review them very quickly. And then, because they're all totally interesting, at some other point, I'll discuss really their story in gory detail, because they're all a lot of fun. So, starting with this. There's our sun. There's our sun. I will skip the part which tells you how we know how far the sun is away from us. You think that's obvious? It's not. The sun is a certain distance away from us. What's that distance?
93 million miles.
Yeah. Where did you get that from?
From
Yeah.
second grade, first
Yeah.
grade.
So did I. But it turns out that somebody figured it out once, and then somebody figured it out better another time, and then somebody figured it out better a third time. So these things are magic when you figure out how they did it. It's really beautiful stuff. And it was done. It was. Did he get it in the back? Did he get this? Did you do this?
Sorry.
Yeah. It was done. It was done in 200 BC. In 200 BC, Aristarchus was a guy who figured out how far away the sun is, which is amazing. He got it wrong, wildly wrong, but he got it wrong. And he said, you know what? If the stars out there are suns, and they're so much dimmer, I can imagine how much further away they are. So he, in 200 BC, knew the universe was large. He knew that. The Greeks, he was a Greek. You think if
sigmas did he have?
what?
How many sigmas?
He was a smart guy.
4 or 5 sigmas.
Yeah, he was 5 sigma. He was a smart guy. So we started out with the sun, the distance to the sun, but we knew that over 2,000 years ago, just not accurately. Now, and the distance to the moon, the distance to the planets, we know all those things now. The distance to the nearest star. How do we know the distance to the nearest star? Well, it's easy. Because the Earth goes around the sun once a year. And so from this position, Alpha Centauri is over here, and from this position, Alpha Centauri is there, and that's called parallax. So parallax. So as the sun moves around the sky, you can see Alpha Centauri move in the sky, and so you can figure out exactly, based upon just geometry, how far Alpha Centauri is, and you can do that for the nearby stars just by looking through an Earth-based telescope. Good Earth-based telescope. So now so you can see the nearby stars. But we're talking about a universe, and the universe is a teeny bit bigger than the nearby stars by a factor of 10 to the 18th. So what we need is maybe 10 to the 15th, but certainly the universe is a lot bigger. How do you figure the distance to all those other places in the universe? And that is a conversation that we're not going to have more than just a cursory explanation because of all the beautiful questions you asked me today. So what we're going to do is just simply summarize, and this is it. A few years ago, maybe 10 years ago, we launched a satellite, and that satellite, very precise, was able to look out and see millions of stars, and it was able to plot the nearby stars. And this circle here was how far that satellite could see. It could see this far, no further. But we launched, that was Hipparchus. We launched another satellite called Gaia, and it's been out there for maybe 10 years, and it's been sending back data, and we've gotten data twice from it. In the second data release, everybody went bananas because it came back with over 1 billion stars. We're able to see, this is not impressive on one level and very impressive on another. We were able to see 1% of the stars in the Milky Way. 1%? Yes, 1%. It's over 1 billion stars. So we were able to see 1 billion stars and the positions of millions and millions, tens of millions of them, maybe hundreds of millions of them, positions of them, where they are in the sky. So now we can see this far. This is our galaxy. We can now see this far, and we know this much information about where things are in our galaxy. That's a lot. That is a lot. We know where things are everywhere in this space. So, but we haven't left the galaxy yet. And we're this little thing that I draw on the screen here, we're talking about down here. Okay? Almost nothing. So we got nowhere so far. In order to get somewhere, you have to leave our galaxy. You have to go to nearby galaxies. And nearby galaxies, the nearest one, the nearest big one is called Andromeda. And Andromeda, when you put that on this graph, I'll now pretend that this graph has been expanded. Okay, so I'll pretend that this is much, much bigger. So Andromeda is like out here. It doesn't belong on the graph at all. It's going towards us, not away from us. You have to ignore Andromeda because there's a lot of things close by that are really they're not worth mentioning because they're traveling with us, and when they're traveling with us, some come with and come away, and you can't count the ones that are close. You have to go far away where things are moving fast away from us, where Andromeda's speed towards us doesn't count. And finally, so you go out here, and these galaxies here, and you measure the distance to these galaxies. And I could leave it like that and nobody's going to ask me a question. I'm just going to walk over this and I'm going to say, measure the distance to these galaxies. And then using that, you can measure the distance to these galaxies. And nobody's asking me a question. You want to ask a question? The question is how? Okay? The question is how? Okay? And it's right here on the screen. Cepheids. Okay, Cepheids are the answer. Cepheids are a kind of star that starts out, that spends its life pulsating. It pulsates with a period, on and off. And afterwards, when that same Cepheid is found here, we find that the Cepheids can be recognized being the same type of star. Their period relates to their luminosity, and so they can tell the distance. I'm going to stop now because I lost half the audience.
I'm still awake.
I know, but there's no reason to bastardize this conversation. This is the conversation that I was going to have at the beginning of this lecture. Okay,
How come Andromeda's coming toward us? Are we going to clash with that?
Yes, we are going to hit Andromeda. Andromeda is going to hit us. But the reason it's coming towards us is because there's this thing called peculiar motions. Okay, if everybody, let's say we had 100 people in this room, and I said let's march down to 42nd Street, and we'll protest climate change. So we'll all go down to so we're all walking towards 42nd Street. But the fact is that not every one of us is moving at the same pace. And some of us are moving left and right as well as down. Those would be called peculiar motions. We all have a motion more or less in the same direction, but there's still individual motions. It's just a small compared to the large motion. Nevertheless, the nearby galaxies don't move away from us very fast. The faraway ones do. So a nearby one isn't moving away from us fast on the average. And so the fact that it's going this way is actually larger than the average motion.
What happens when we bump into each other?
We collide. And then we go our separate ways. But we come back and we do this until we become one galaxy.
We destroy a lot of stuff.
We don't destroy anything. We make new stars.
Isn't it possible that we are moving toward Andromeda rather than they to us?
Same thing.
No.
There's no place in the universe which is at rest. So there's no place except what you define as being where at rest. You you and you alone, are the center of the universe, okay? And everything in the universe is moving towards or away from you, okay? So Andromeda is moving towards you, okay?
So it's as valid to say that we're moving toward it as it to us.
But better if you were standing on Andromeda, then you'd say, well, Milky Way is moving towards me. There's no proper motion. There's no standard of rest in the universe. Now, I have said this in this class many, many, many times, but the problem is it can't be understood easily. And the person who sort of had something to say about it that made a little bit of sense was a guy named Einstein. And do you remember his general theory of relativity? The word relativity, which is maybe not the best word for it, but really the reason it's sort of stuck in there is he's saying is everything that we're talking about is relative to the arbitrarily defined point which is at rest, and everything else is relative to that. Mm-hmm. And any point in the universe can be considered to be at rest, and the laws of the universe will be the same no matter where, because they will be the same laws relative to that point. So that's where the relativity comes from. And it's over 100 years old, and most people haven't gotten it yet.
So what's the constant that they keep talking about?
The constant?
Yeah, that he said it was there, and then he said it wasn't there.
Okay, so Einstein has a set of equations. The set of equations turns out to have a small little problem in that they're unstable. They predict a universe which is either expanding or contracting. There's no way to get the universe to be static unless you insert a constant which is designed to prevent the universe from expanding or contracting. So if you stick in that constant, called the cosmological constant, then you can prevent the universe from contracting or expanding. So he's inserted it, but it turns out the universe was expanding. And so he made a mistake by sticking it in the first place, because he thought that he had wrongly inserted this constant. As it turns out, since the universe is expanding at an accelerating rate, that constant, which he thought to be wrong, could be responsible for the accelerating expansion of the universe. So Einstein is back having 100% on his final exam.
I don't understand.
Okay.
He made a mistake that turned out to be true.
No, I mean, if the universe is expanding, what's the constant?
The constant is the thing that's the constant. If the universe is expanding, it's plus. If the universe is contracting, it's minus. You add the number that brings whatever that rate is to 0. Then the universe isn't doing either. So he inserted that number. He didn't know what the number was, but he inserted it, and he said that number will keep the universe from expanding or contracting. There you go, I'm done. And then they discovered the universe was expanding. And then they went, oops. And then, of course, he had said it already, so he couldn't take it out of the equation. So it's always in the equation, because it's Einstein's equation. And now it's better. It works. People like it. They just don't know whether dark energy is that number. So the controversy is whether or not did Einstein's constant, is that the same as dark energy? And we're still trying to figure it out. Because when people try to figure out what the constant should be, they always calculate it, it comes up wrong. Dark energy is a different number. Who knows? Anyway, so I guess that's it. Barbara, do you see the dates up there?
No.
Come take a look.
Are you putting it in an email?
I put it in the email I already sent you.
From yesterday?
Yesterday.
Yeah.
Right.
Be safe on your journeys. Be
Yeah.
safe. Yeah,
Thank you.
that's not trivial.
No. What